All right, thanks everybody for joining us today. We have our last enrolled speaker, but we do have one more speaker in the series this semester. Alan will be speaking with us after the break. But I would like to welcome Yuqi Huang, and he'll be speaking to us about his Ph.D. work here at the University of Oklahoma, where he works with Dr. Wang. He'll be working he'll be speaking to us about urban canopy models, yes. And so we'd like to welcome him to the series, and I'll go ahead and let him get started.
Yeah, thank you. Well, hello everyone. Good afternoon for joining here today. My name is Yuqi, and I'm a second-year PhD student working with Dr. Chenghao Wang. And I'm gonna present today is multi-parameterization of hydrological processes in a single-layer urban canopy model. And today I'm gonna focus on these three topics. The first is why do we need to study the urban hydrological processes? And the second one is how do we improve water balance or hydrological representation in a single layer urban canopy model? And finally, I'm gonna talk a little bit about my ongoing work or future work. So I hope by the end of this talk, I can convince you some of these questions. So let's get to the background. So we are living a more urbanized world. Urban areas actually accounts for only 5% of the world's territory, but accommodating over half of the world's population. And it was estimated that by the end of 2050, there will be more than 2/3 of the world population residing within the urban areas. And with the warming climate or climate change, there will be an increase in extreme events within urban areas, such as urban flooding, urban like droughts, etc. And we have already seen such kind of disasters in the breaking news. And also, land surface models are essential tools to understand land surface processes and also land atmospheric interaction. And urban land surface models, or ULSMS, are one of those tools to understand the urban climate, especially urban land surface processes. And they are also important tools for urban planning and to come up with adaptation strategies to address issues like increased urban heat island, etc. And generally speaking, there are three main categories in terms of urban land surface models. Those are one-dimensional slab model, and the slab model, they take urban areas as a flat plane, and these are commonly used in many of the weather models such as HRR. And also, there is two-dimensional canyon model, which is urban canopy model. Well, they take complex urban geometry as a ground bordered by two facing walls. And the most complex is the three-dimension urban model, which they have multiple vertical layers. And based on your research purpose, those urban land surface models can focus on those three main processes, such as the first is momentum or airflow exchange. The second one is the energy flux or energy flux based on surface energy balance equations. And the third one is more focused on the mass or the calculation of water fluxes based on mass balance equations. And today my model will be focused on the two-dimensional single-layer urban canopy model with a focus on energy flux and water flux. And there are many urban land surface models. So there are three kind of urban land surface model intercomparison project to help us understand whether those different models perform well or bad. So the first intercomparison project can date back to over 20 years ago, which is called PIL-PS Urban. And they found that actually no single model performs well across all the fluxes. However, this situation has been improved in the second intercomparison project, which is finished last year. It's called Urban Plumber. And the conclusion drawn from that project is there is significantly improvement in the urban land surface performance in terms of all kinds of fluxes. And also, actually, complex models are generally outperformed by the single ones, especially those like two-dimensional canyon models. And there is an article published early this year, which the author focused on to explore the water balance representation in urban plumber land surface models. Well, they found that the water balance appears unclosed in about 43% of the model runs, which can undermine their accuracy in simulating the water or energy fluxes. This is because most of those urban land surface models lack or oversimplified the hydrological modules. And actually, this also is the research gap of this project, which we aims to enhance the urban hydrological processes. And can find, with this, we can finally capture better capture the urban land atmosphere interaction and also improve the regional climate simulation. And next is the model development. So the model I introduced today is actually based on a model called Arizona State University Single Layer Urban Canopy Model, or ASLAM in short. Actually, ASLAM model has undergone several periods of development, and the latest version is called ASLAM version 3.1, and it was developed by my advisor, Dr. Wang. And ASLAM can simulate urban land surface processes such as comprehensive urban canopy layer heat exchange, for example, latent and sensible heat. And also it takes into consideration of subsurface heterogeneity. For example, we in this ASLAM version 3.1, we have four types of ground, that is concrete, asphalt, vegetated ground, and bare soil. And it has a basic hydrological processes. For example, it can simulate the evaporation and the infiltration of the ground. And it also has green roof, urban irrigation, and anthropogenic heat module within it. And the most important is it has already incorporated urban vegetations or urban trees so that we can simulate their biophysical processes, such as the tree shading effect, the evapotranspiration of the urban trees or vegetations, the root water uptake, the tree canopy transmittance with interaction with the complex urban geometry. And here I introduce the ASLAM Hydro, which has enhanced hydrological module compared to the ASLAM version 3.1. So in ASLAM Hydro, we incorporate multiple hydrological parameterization schemes. And in this way, the model can complement its existing capabilities of resolving the like root water uptake, evapotranspiration, all kinds of basic hydrological processes. And also it captures some other key hydrological processes, such as the canopy interception by urban trees and grasses. It also enables the subsurface runoff calculation, and it improved the surface runoff and the soil moisture dynamics processes. And the aim of such a multi-parameterization or the enhanced module is first to better represent the hydrological process with more accuracy tailored for a specific city. And the second one is to facilitate further couple with mesoscale or global models such as WRF, MPAS, and CESM. And multi-parameterization hydrological scheme actually represents those 6 different soil hydrological schemes. They are the default scheme, the shake scheme, the VIC scheme, or variable infiltration capacity, the M-Xianjiang or modified Xianjiang scheme, the BAT scheme or biosphere atmosphere transfer scheme, and the ETOP model, which is top model with equilibrium water table. And those plots are runoff soil water curves featured by different hydrological schemes. We can see basically to just describe the relation of saturated soil fraction with either runoff or infiltration capacity. And here is a detailed table which summarizes the characteristics of each individual schemes. So we can see that for all of those schemes, it can output the surface runoff, and depends on each individual scheme, it can output like saturation fraction or maximum infiltration capacity as well. And almost all those schemes depends on soil water content. And in order to run those different individual schemes, you have to decide their parameters first. They have different depending parameters as well. And we consider two surface runoff mechanisms. Those are infiltration axis runoff and saturation axis runoff. And there are two subsurface runoff schemes, which are bottom drainage due to gravitational loss, and another is subsurface runoff based on equilibrium water table. And then we tested our enhanced hydrological module, which is Slum Hydro, against a single site, which locates at Basel, Switzerland. And we use the data obtained from the field measurements at Basel Urban Boundary Layer Experiment, or BUBL. Basically, we run a month simulation from June 10th to July 9th, 2002, and there is 1 day spin up. So here is the basic site information. You can see, like many other weather models, we have air temperature, wind speed, wind direction, relative humidity, short wave, long wave, downward radiation, air pressure, and precipitation as our forcing data. And those data are acquired from instruments mounted on the top of this flux tower, which pop up into the inertial sublayer. And we also have in situ data within the urban canopy layer, such as this height. And then is the overall result. We can see this is the summary of performance using different versions of a slum. So if you compare version 2 and version 3, you can see generally version 2 can reproduce sensible heat flux, but they perform bad in latent heat flux. So we can see including urban vegetation or urban trees is very important. And if you we compare a slum hydro with version 3, we can see there is a broader improvement in latent heat and sensible heat, so that we can conclude that capturing key eco-hydrological processes is very important. And if we compare the performance of different schemes, so the left figure is the indices of performance across 6 schemes in terms of TCAN, canyon temperature, LE, latent heat, HU, sensible heat, and RN, net radiation. Actually, all those schemes exhibit comparable well performance at Basel site, at least. And the right one shows the runoff response to precipitation for those different schemes. And the generation share also similar patterns within those 6 schemes. And we also take a look at the water balance closure or water partitioning conditions. So here, in terms of water balance closure, we assume that all water fluxes should add up to 0. That is, the source term should equal to the sink term. And the only source term is the precipitation in our case. And a sink term can be like evapotranspiration from the roof, from the intercepted rain, from the tree, from the ground, and the subsurface runoff and surface runoff, and also the final one is storage term. And we can see that the water balance is closed in all the 6 hydrological schemes with a mean residual of only 0.38%. And if we take a look at those individual bar plot, you can see the water partitioning exhibit similar patterns across all the schemes. And the largest thing term seems to be the surface runoff, and followed by evapotranspiration from the ground and then from the tree. And if we take a look at the red box here, you can see we also captured evaporation of the intercepted rain. So this can tell us 2 things. The first is with enhanced hydrological module, we can better represent more detailed urban hydrological processes. And the second one is it also proved the potential of urban vegetations or urban trees as a mitigation strategy to address those urban environment issues such as increased urban heat island or urban overheating, etc. But yeah, you may ask why there is no significant differences among those different hydrological schemes. So for this, I have 2 hypotheses. The first one is, I think the performance, the impact of those schemes on the model performance may depends on different site and depends on different background climate. So for example, if we test our model at like dry conditions, such as in Phoenix City, there is already almost no precipitation, then how can we anticipate there is any large difference within those different schemes? So in order to address this, we have to pick up more sites to address or to account for these various background climates and site characteristics. And the second hypothesis is that the impact of those different schemes cannot be fully captured with such a limited simulation period. So we need a longer simulation period to better evaluate our enhanced model. But before we start to test our model against global sites, we have to consider one thing, that is the role of initial soil moisture. Because as you may know, the impact of initial soil moisture status is quite important, especially in weather forecasting. And those impacts may last for several months or even longer. So here, I set different experiments with different initial soil moisture to test the model still at the basalt site. So here I select 5 initial soil moisture status that is at the residual soil water content and equal to 0.15, 0.25, 0.35, and at its saturated soil moisture. And we can see that, so the first one is canyon temperature. That canyon temperature is less affected by the initial soil moisture because all those lines are kind of overlap. But initial soil moisture has a greater impact on the urban latent heat and canyon-specific heat simulation, especially towards the early runtime periods. Right, we can see the diversion of all those different curves. So we can draw the conclusion that the initial soil moisture conditions are really important if we want to run a long-term model. So with that bearing in mind, now we can test our model against the global sites. So first, our data is acquired from this Urban Plumber, still the Urban Plumber project. So in this project, they have like 22 global sites, which are various or separated across different background climate. And those data are acquired from urban flux towers. And those are open data published by Lipson et al. And for each site, the observations are prepended with 10 years of aerophile-derived meteorological data to allow modeled variables such as soil moisture or ground temperature to equilibrate with local climate conditions during the model spin-up. So we run a 10-year spin-up for each of those 10 sites. So there are 22 sites, but for this project, I choose like 10 sites to test it. And we run 10-year spin-up for each 10 sites to get the soil moisture and ground temperature, roof temperature, and wall temperature at the last time step. And we take this as initial condition for our observation period runtime. So here is a example of the result of model spin-up at Preston in Australia. We can see that, so this one is vegetated soil moisture. We can see the soil moisture continue to decrease until like half months later, it reaches like close nearly to the real conditions. So the initial conditions will impact the model performance for at least half months in this case. So after we run 10 years spin up for each site, we can see the overall performance of the of different hydrological schemes against global cities. So this is a radar plot of the model performance across 10 global cities. And if you take a look at the bottom right, the net radiation exhibit the best performance across all the sites, nearly 1. And followed by sensible heat and latent heat. And from those kind of parallel lines, it's not hard to find that, again, all schemes generate similar performance across global sites. And we also compare the impact of those different schemes on model performance to see whether they depend on like impervious areas fraction or precipitation. But unfortunately, we find no strong enough relation of the model performance in terms of either precipitation or impervious area fraction. So it seems that the impact of different schemes on model performance is independent of land use and background climate. But this is still to be explored because I just run those periods during the whole like wet year and dry year. I didn't separately run on whether on rain days or no rain days. So it's still I cannot draw this conclusion easily. But yeah, this also makes me think whether there is other physical processes that matters more in terms of influence the model performance. For example, maybe the different soil dynamic schemes may matters more in terms of altering the model's performance. This is to be further explored. And in terms of water balance closure or water partitioning, actually we can see different hydrological schemes show significant difference in water partitioning, especially in terms of runoff generation, which is marked like pink in this bar plot. And for each site, there are actually six bar plots, but they are kind of squeezed together for better comparison. So, and also this kind of impact tends to be more obvious in either dry climates, such as Phoenix, or in cities have higher precipitation regions, such as like Vancouver and Baltimore. But this is just a pure observation. We need further exploration in terms of this phenomenon. And also, we found the Vic scheme yield a slightly higher runoff on average, and followed by BATS and the ETOP model. So actually, those different schemes may have a significant influence on runoff infiltration generation relation. Yeah, so here comes to the limitation and takeaways. So in the current slum hydro, we didn't consider the snow dynamics and the routing schemes, since we are more focused on the energy flux simulation. So there's no routing, but in future, yes, snow dynamics is definitely needs to be considered. And also the specific runoff scheme can be further improved with a detailed global water table data set. So currently, the ETOP model, which is the only scheme that requires the water table. So the water table is like hard-coded in our current slump hydro. And yeah, but here is the takeaways. We advanced the hydrological module within the urban canopy model to better represent the detailed hydrological processes. And turns out we improved the water and energy flux simulation. And different hydrological schemes may have greater impact on runoff generation than energy flux simulation, which needs to be further explored. And this can be done by separately run on rain and no rain days. And finally is some of the ongoing work. The first one is I'm currently trying to improve the representation of biophysical processes in the WRF single-layer urban canopy model, such as like canopy interception, root water uptake, and the radiation exchanges. Because currently, the land surface models used by WRF, they didn't consider any urban vegetations or urban trees. So this is kind of problematic because they tend to predict higher air temperature within those urban areas. Yeah, this may be related to the problematic energy partitioning. And the second one is to enhance the urban hydrological simulation in single-layer urban canopy model using such a multi-parameterization scheme, and to couple it with the NOAA MP land surface model to address the sub-grid scale heterogeneity in urban land surface, in urban land use. And yeah, so here is the acknowledgement. Yeah, I greatly acknowledge Dr. Chenghao Wang for his idea and support in the development of slum hydro, and also thank Dr. Zhihua Wang for his insightful suggestions in the model development. And also I thank all the NWC 5340 office mates for their support. And finally, I would thank the use of all the data sets in this project. And with that, I'm gonna end my presentation and open to any questions. Thank you.
So we can go ahead and open the floor for questions. Anybody in the room or online has any questions?
You mentioned that the SLAM hydro has like 3% or fat culture error, right?
I think is point. Yeah, it's right.
Okay. What's the performance of other hydrological urban model that hydrological? That's like
So actually, in the latest intercomparison project, which is published early this year, they find like there are 19 urban land surface models, and the water balance is unclosed in almost 43 of the are within the 3% error. Yeah.
I think that's slide number 9. I think that's like a question about that.
This one.
So these are the different electrical models.
Yes, schemes.
So are these time dependent or prognostic models?
I think they are not prognostic models.
So they're diagnostic.
Yeah.
Okay. But do you still have like a grid or Z? You have are you solving at different levels in soil?
Yes.
How many levels do you have?
So in the slump hydro, we have 10 layers for the ground and 5 layers for the roof.
What is how big are the layers of the ground?
The total depth, you mean?
Well, the distance between the grid.
So actually they are not equally.
Okay.
So on the topmost, maybe like 0.1, and in the bottom 5, like 0.2, 0.2 meters.
So how do you initialize your model, soil model? How do you know what's putting down?
Yeah, so for the basal site, we have our measurement data for the soil moisture, but for the global sites, we don't know the initial conditions. So I just set for example, the soil moisture to be at its saturated soil water content and run the model. But we believe after 10 years of spin up, the result will be like approaching the realistic conditions. So that's why we need to run such kind of long time spin up.
So if you're going to run it a long time, though, eventually you need to deal with the lower boundary condition. You mentioned this diagram shows bedrock. So is that your lower boundary is bedrock?
Yes.
Okay, so does that mean that putting bedrock in 2 meters down everywhere?
Yes. Currently, yes.
Have you tested the sensitivities for that long time run?
Yeah, not yet, because actually the 10 years run is quite computationally expensive. So we didn't have enough time to do that test. But yeah, I take this as a very good suggestion. It's definitely worth to see it. Yeah.
You mentioned
Just a slum model. It's just an offline test. Yeah, because we want to first make sure that our model is quite, how do you say that, is quite validated. And then with this enhanced module and validated module, we can like couple it to the WRF model. We just first test it offline.